Oh boy. First off, this meme made me laugh. I don't know what that animal is. It's not a turtle. There's no shell. I thought that too. Is it a frog? I thought it was a frog. It can't be. There's no shell. It can't. The spine of the turtle runs along the shell. How do they grow out of their shell? They don't grow out of their shell. Their spine is integrated into their shell. Frogs? Yeah. A what? There's no way that thing has legs. Okay, so we were talking about EMFs. Now we need to talk about EMFs that give a signal you can actually measure. So sinusoidal EMFs. First off, math term, literacy challenge. What does sinusoidal mean? Sinusoidal. What kind of pattern would a sinusoidal signal have? Yeah, it's a sine wave. You couldn't say it, but you did the right motion. Well, that or you have movement Tourette's. I don't, but so now if we start with so then our EMF and yeah, this is one of those places where the book just kind of skips a bunch of steps and goes, here's the equation. But we're not doing that. So you have to use derivatives and get used to the trigonometric round robin. Because here's how the derivatives of sines and cosines works. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. The derivative of negative cosine is sine. It's round and round and round and round and round. Yeah. Yeah. We put tangent in the corner. Yeah, it's not fun. Okay. Now, not the most straightforward derivative. I'll show you how it works. I mean, in the future, if you practice it enough, you'll get it down. Takes a little bit. Because the cosine of omega t is a function of t, but I can't just take the straight derivative because I have that omega in there. Well, I'm trying to figure out how to say that, like, because I know that like with you guys, everything's a minefield. If I say something the wrong way, you're going to take it and go off on some weird ass tangent. And huh? Yes. So you have to use a process called U substitution. The way we do that is we say that we're going to have U equals that whole omega t. So the derivative with respect to t of t is just 1. Okay, so, and then we have kind of a little chain rule. Where we're going to use so basically we're taking our d dt, putting du, that's going to give us so we just end up with those two derivatives multiplied by each other, and we already have du dt. So now this is going to be, so now your d dt of, and your BA are constants, so they pull out front of cosine. Omega t is going to be cosine of u. And the derivative of cosine is negative sine. Our du dt is omega. So now that's going to be negative. Well, let's do it this way. So we have the du dt, which is omega. Negative sine of u. And then we can just plug back in what u is. And we get a negative omega sine omega t. And so every time we take a derivative, we're going to get another factor of omega out front. Once you get used to that process, you can just say, okay, yeah, so if I took another derivative, I'm going to get omega squared. And then once I get back around to, through cosine, then the sign out front will be positive, so on and so forth. You're just going to keep getting omega squared, omega cubed, omega to the fourth, so on and so forth. And so what this ends up being is see, that's why I have to be careful. You guys have the attention span of George W. Bush. Today in the economy, oh, look at the kitty. George, focus. There's a kitty. No, focus. It might be. So this is going to be, so we get this negative sign to cancel out the negative. You're going to get the omega. So you're going to get omega. The thing that's really too old for you is that joke is an homage to Robin Williams. And so this is what we mean by sinusoidal EMFs. This actually gives a signal that you can measure. Okay. So here you go. You have a rotating coil generator. The magnetic field between the poles of an electromagnet is 0.4 Tesla. A circular coil between the poles has 120 turns and a radius of 4 centimeters. The coil rotates with frequency 5 hertz. Find the maximum EMF induced in the coil. Okay. So we know that this rotating coil produces an AC current, which is going to give us a sine wave. Okay, so now the question is, where's the maximum signal? The maximum EMF will be at the maximum signal. Where is that? The peaks. So your amplitude. And at your amplitude, what is the sine function equal? Yeah, so somebody over here kind of mumbled it, but yeah, it's 1. So your sine function equals 1. So now we just have to figure out what each one of these numbers in and plug them in is and plug them in. So our area is going to be pi r squared. Okay, so we have A. Now, remember, omega is your rotational frequency. Okay, so that's radians per second. We were giving a frequency of 5 hertz. Do you remember how we connect frequency to rotational frequency? Yep. So our omega is going to be 2 pi f. So for us, it's 2 pi, 5.0 hertz. 31.42 radians per second. Okay, so Emax is now going to be 31.42 radians per second, 120 turns, 0.4 Tesla, 0.00503 square meters. 7.60, what's the unit? Tesla times meters squared per second is Webers per second. Oh, you just wait. In inductance, we're going to use Henry's. Now, joules, think about EMF is in what units? Volts. Remember, your volt is your Webers per second. Okay, Lenz's law. This one's harder to visualize. So this is about a changing magnetic flux through a surface, okay? So as magnetic flux changes through a surface, so like in this case, you have a coil. The current induced in the coil will move in the direction that causes a magnetic field that resists the change in flux. I don't know, I just Googled that when it was on there. I guess this is a real problem. Oh, believe me, I know every single day you've had a test. So, let's try to think about that. So a bar magnet, if it's not moving, the magnetic field going through the ring, it's not fluxing. You're having to have magnetic field moving through the surface to have a flux. That'll happen. So it's Freudian slips because you're all pissing me off. Now, the hard thing about this is, so let's say, so you have your magnetic field going through this way. You pull the bar magnet back. That means the flux is retreating the opposite. So it's going that way through the surface, okay, through that area of the ring. There will be a current induced in the ring in such a manner that the magnetic field circling around that ring is going to resist that change in magnetic flux. So that means the magnetic field produces has to point that way. And so if I do that by the right-hand rule, it has to wrap that way, the current has to go that way. Just know that you find the direction of change in flux, and then the current you are looking for is going to resist that change. This is how, like in your computer, this is how inductors work. Because in an inductor, you get that change in magnetic field, which induces a current, which is going to resist that change in field. But most of the time, the field is originally generated by a current going through the inductor, which then causes a back current through the same inductor. It basically regulates the energy flow through that part of the system. So this one's a little harder to visualize. We're all having so much fun with magnetism. That's the easiest way to do this one.
No. Yeah. You think you can't survive?
Yep.
Are we talking? Party.
None of you under 21 better be partying hardy. Especially now. Okay, so that's not a clown. Yeah, it'll be online. So we have an external magnetic field parallel to the center axis of a 50-turn coil of radius 5 centimeters. During an interval of 160 milliseconds, the field changes from 0.2 Tesla in one direction to 0.3 Tesla in the opposite direction. The resistance of the coil is 82 ohms. What is the average induced current in the coil during this time interval? All the formulas you've had up to this point. You know the change in the magnetic flux. Okay, so what is the average induced current? And how am I going to figure this out with the resistance of the coil? Honestly, I could ask this one question and that'll decide like A or F for the semester. And you all better be studying because the Shattern State policy, an 89.99 is a B. And it's a policy. Well, most schools care enough to round you up to an A. No, no, we do. Yeah. Every school has experienced an enrollment drop off over the past like 5 years, but no, it hasn't been this year. You have to stay away from the social media rumors. And not this year though. Okay, so my first question is how do I relate voltage to current? Voltage to current involving resistance. How do I relate voltage to current where I include resistance? There you go. Hey, spirals, anger management. Watch this. You guys have street names now. No, the one next to you. No, if you were going to have a nickname, it'd be Lebowski. If you were going to have a nickname, it'd be Lebowski. Because everything that happens, you just sit there going, that's just like your opinion, man. So your anger's gone. Shall we bring in Brandon for a questionnaire? Okay, so this means that the current we're looking for an average, so we're just going to go for that absolute value. Oh, not over I, over R. There we go. 1 over R. And so then it's going to be in oops. So we're at least starting here. So then we have to think about the change in the magnetic flux. Okay, so really? We have the same coil.
So annoying. You mean blood? Oh, yeah, I see, just a little blood. Yep. Yeah, yeah.
So at one point, the magnetic field is fluxing one direction. Next time it's fluxing in the opposite direction. Okay, so, and the field being parallel to the surface area or the cross-sectional area, what angle is theta? Nope. 0. Because remember, if we were doing oh, you just wait. An attitude like that, we're gonna have some fun.
I was just saying.
Oh, okay. So our area vector is always going to come off perpendicular to the cross-sectional area. And so in this case, we have a theta of 0. You could say 180 and get a -1, but again, we're looking for an average value. So we're just going to absolute value that whole thing anyway. So since theta is 0, our current is now going to be N times A times the change in B, because cosine of theta became 1. And then of course our A, pi r squared, turns pi. The radius is 0.050 meters squared. And then our change in B can be 0.30 Tesla minus a negative 0.20 Tesla over 82 ohms, or as this class has come to call them, funky squids. Octopus, yeah. And 0.16 seconds. So our current is going to be 0.0150 amps or 15 milliamps. Oh boy, inductance. So we have self-inductance and mutual inductance. Here's an example of mutual inductance. You have a current in one coil, produces a magnetic field. That magnetic field reaches out and touches another coil and fluxes through that coil, which then induces a current in the second coil. Coil 1 gets current, produces magnetic field. Magnetic field touches coil 2, produces current. Does it what? Yeah, the current in the second one will be produced by the magnetic field from the first one. We also have self-inductance. So again, this is like the inductor in your computer. You have like a coil of wire, a current starts flowing through it. That current produces a new magnetic field in that coil. That new magnetic field then produces a back current, a back EMF, to compete against the EMF being put into the coil to produce a magnetic field that fights against the new magnetic field produced by the current that's been put into the coil. So you have coil, current goes into coil, produces magnetic field. Coil does not like magnetic field, produces own current against current to create magnetic field to fight against new magnetic field. By creating a back current inside of itself. So it technically has current running both ways in the same wire. So it's fighting against each other. That's called a back EMF. So again, this is all coming back to Lenz's law. You know, for a second, I forgot that you had set pizza on that napkin. And I looked down and saw it, thought it was your tissue. I was like, what kind of infection do you have? Okay, so I don't think you want to play that game. Most of the time I am doing physics up here, where the entire class I hear, no, you're not. And you don't have it. Okay, so to get to our induction equation, we're going to start back. We're going to start back with Faraday's law. Okay. So we remember that earlier we had an equation, our magnetic field. Only this time we're going to change it to your lowercase l is going to be the length of your length of your coil cylinder now. This will make sense because capital L is what we use for inductance, so we can't have that all over the place. Huh? Mu zero. Okay. Now we need to remember Faraday's law. So first off, we have our area vector. Current is going that way, which is going to induce a magnetic field. So we're going to get magnetic field wrapping around the wire that way, where we're going to have magnetic field vector like that. So what is theta? Nope, 0. B and A point in the same direction. So cosine of theta becomes 1. Now, for a coil of n turns, we're going to get n times phi equals n times the magnetic field times the area. But we have that for magnetic field. Hmm. Move this around a little bit. And so where we end up is our equation for inductance. And then, of course, your L is either going to be that's one equation for inductance. That's your other equation for inductance. The SI unit for this Weber per amps or volts second per amps equals H. Henrys. It is, yes. Is that how you spell it? Maybe that, I don't know. Yeah, so it's one of those. The dude's last name is Henry that worked with inductance. Now, what about EMF in terms of inductance? EMF in terms of inductance. So if we remember, our EMF becomes negative L delta I over delta T. That's your induced EMF in an inductor. Okay. Inductance in a solenoid. So let's go back to do you remember what the small n is? It's the one. Well, it's the number of loops per unit length. Or we can say that N is N times L. So if our inductance we can plug in the N times L, mu 0, N squared, L squared, area for L, we're going to get mu 0 L squared A, or L times A. What does A equal? Yeah, pi r squared, circular coil. So that's one form of it. Or so that's going to be inductance inside of a solenoid. So you'll either have number of loops or number of unit loops per unit length. So inside of your, this is an example of a few types of inductors inside of machines. Inductors can also store magnetic energy. That just sounds fun, doesn't it? So we won't make it all the way through this, but what stored energy is going to be a change in energy over a time rate change of energy. What do we call that? Change in energy over change in time. Nope. Power. So that's what we're trying to find. So in this case, to avoid assumptions that we don't want to make, the power stored in the inductor so remember our definition for the change in work over change in time is going to be V times I. And of course, our EMF, negative L. Now that's negative, but this is an internal EMF. If we're storing power inside the inductor, we need an external EMF, okay? How does E external relate to E internal? Remember, the E internal is trying to fight the external EMF. So how do they relate to each other? Yeah, so negative the internal. So that's going to be a negative. So it becomes positive. Okay, and we'll finish this the next time. We'll finish this on Friday, probably finish the chapter, but